Okay, welcome back to another installment of Chemistry with Bandit. Say, Bandit, are you ready to learn some chemistry today?
Oh yes, Mr. Hopper, I love chemistry.
Alright, Bandit, we'll tell the audience who you are.
I'm your nephew's dog, Bandit. I like chasing cats and chemistry.
Alright, well, today we're going to be looking at electron configuration. So recall from the previous module that an orbital shows the probable location of an electron that possesses a specific amount of energy.
Wait a second, what is this energy thing you speak of?
Well, as it turns out, an orbital can also be thought of as the amount of energy an electron must possess to be in that orbital. If the energy of the electron changes, the electron will change to a different orbital. Sometimes these orbitals are referred to as wave patterns. So when an electron changes orbitals, they're not moving to a new place, they're only changing their wave pattern.
Oh, thank you, Mr. Hopper. That makes a lot more sense now.
In atoms that only have one electron, the energy of the orbital only depends on n. The lowercase n is used to represent what is called the principal quantum number, which tells us which main energy level or shell we are dealing with. Just remember that n is the shell number. In atoms with multiple electrons, the energy of the orbital depends on both n and l. N is the quantum number that tells us the shell, while l is the quantum number that tells us the subshell. We will learn all about quantum numbers later on. In other words, the energy of an orbital depends on what shell and what subshell it's in. Therefore, we're going to have an energy difference between the different type subshells S, P, D, and F of the same shell. So the 3s subshell will have a lower energy than the 3p subshell, which will have a lower energy than the 3d subshell. However, the orbitals in a particular subshell will have the same energy. When orbitals have the same energy level, they are said to be degenerate. So when talking about the orbitals of a specific subshell like the 3p, we would say that the orbitals of the 3p subshell are degenerate.
So what is the difference between atoms with one electron and atoms with multiple electrons?
Well, that's a good question, Bandit. The difference comes from the added repulsive forces between the negatively charged electrons. Remember, opposites attract, so like charges repel. The outer electrons are pushed further away from the nucleus by the repulsion of the inner electrons, thus weakening the attractive force between the nucleus and the outer electrons. This is known as shielding. Shielding causes the required energy that an electron must have to be in that orbital to increase. Shielding is what causes the orbitals of different subshells to have different energy levels. The energy diagram on the left shows the subshells in order of increasing energy levels. By knowing the order that the energy levels fill in with electrons, we can predict how the electrons are distributed in the atom. This distribution of electrons is known as the electron configuration. If the electron configuration has all the electrons in their lowest possible energy level, we can also call it the ground state configuration. The Aufbau principle, which is German for building up, basically states that the lower energy orbitals fill first. The order is as follows: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f.
What? You mean to tell me each shell only has an S and a P subshell filled before another shell is added?
Well, that's an excellent question, Bandit, and that's very astute of you for noticing that. That's why the valence shell, which consists of an S and a P subshell, can only hold 8 electrons. So if you'll notice as you go through the order, it always, after it gets to the P, it changes to another shell. So it goes like 3S, 3P, and oops, now we're in shell number 4. And then it goes back and it finishes filling shell number 3. Okay, so the outer shells can only have a maximum of 8 electrons. Luckily, we can use the periodic table to determine the order and how many electrons go in each subshell. Each different block of the periodic table represents the 4 different types of subshells: the S, the P, the D, and the F. The row will tell us which shell that subshell goes with, and each individual element block tells us how many electrons will go in that subshell. Remember we said that the row on the periodic table told us what shell we were dealing with?
Yes, Mr. Hopper, I remember that.
Well, that's definitely true for the S and P part of the row. In the S and the P blocks, N is equal to the row number. Remember, N is the shell number. So if you look at the elements 5 through 10 on the periodic table, that would represent the 2p subshell. In the D block, N is equal to row minus 1. Since the top row of the D block is in row 4, it represents the 3d subshell. In the F block, N is equal to row minus 2. The top half of the part that is pulled out of the periodic table is known as the lanthanide series, and it represents the 4f subshell, since it is pulled out of row 6. It's important to remember that the F block comes out of rows 6 and 7 of the periodic table, and when you follow the atomic numbers, one electron will go in the D subshell, then you will fill the F subshell with 14 electrons, then go back and finish filling the D subshell. This is just the same thing we just looked at, just in a different format. Here the periodic table is joined together as it should be. Outlined in blue is the lanthanide and actinide series. The red arrows are showing the edges of the D block. Here you can see that if we follow the atomic numbers, the D subshell will get 1 electron and then the 4F will start to fill. You will need to memorize how to use the periodic table to figure out the order that the subshells fill with electrons, or you just need to memorize the order. Now that you know enough, we can actually start writing electron configurations of atoms. In electron configuration, the number in front is N, the main energy level or the shell. The letter is the type of subshell. Together, the number and letter identifies the subshell. The superscripted number is the number of electrons actually in that subshell. Remember, a superscripted number is going to be a smaller number that's in the upper right corner. We can usually say that all the subshells are full except the last one being filled. It may or may not be full depending on if there are enough electrons. So remember, S subshells can hold 2 electrons, P subshells can hold 6 electrons, D subshells 10 electrons, and F 14 electrons. Typically, when we are done writing the electron configuration, we want to rewrite it so that all the subshells of the same shell are written together. In other words, everything with the same number would be written together in SPDF order. Now for some examples.
Oh boy, Mr. Habiger, I love examples.
Well, that's a good thing, Bandit. I'm glad somebody does. Welcome back to another installment of Chemistry with Bandit. In today's show, we will discuss orbital and noble gas notations of electron configuration. Say hi to the folks, Bandit.
Hey, Mr. Habiger, I'm really excited to be here. I brought some jokes with me this time.
Well, that's good, Bandit. But why don't you tell the folks your credentials first?
I have a PhD in canine chemical engineering. I'm currently conducting research in solution chemistry.
Well, tell us a little bit about your research.
I make mineral water. I basically walk around until my paws are nice and dirty, and then I put them in the water bowl. The water dissolves some of the dirt, and voila, we have mineral water without the nasty chlorine taste. It's delicious.
Interesting. Well, anyway, back to today's topic. Some of the things you need to remember from the previous modules are lower energy levels fill first. We will use the periodic table to determine the order that the energy levels fill in, and that S subshells have 1 orbital, P subshells have 3 orbitals, D subshells have 5 orbitals, and F subshells have 7. By knowing which section of the periodic table represents which subshell, we can determine the order that the subshells fill in. Remember that in the S and P blocks, the row is the shell number, N. In the D block, the row -1 is the shell number, and in the F block, the row -2 is the shell. When determining the electron configuration, we always start at hydrogen and go through the elements until we get to the element we want. The elements that we go through will tell us which subshells will get electrons and how many electrons they get. Remember, each element on the periodic table represents 1 electron. It is also good to remember that S subshells can hold 2 electrons, P subshells 6, D subshells 10, and F subshells 14 electrons. The abbreviated or noble gas notation of electron configuration uses a noble gas element symbol in brackets to represent all but the last row of the electron configuration. In the example of the electron configuration for barium, all but the 6s2 is the same as the electron configuration for xenon. Therefore, we will replace it with the symbol for xenon in brackets.
Okay, so the electron configuration for aluminum, the element symbol for neon would take the place of 1s2, 2s2, 2p6?
That's exactly right. Good boy.
Who you callin' boy?
Oh, sorry, Bandit. Good job. To find the electron configuration using this abbreviated notation, we would first find the element, then work backwards through the elements until we came to a noble gas. Then we would write that noble gas's symbol in brackets and would start the electron configuration from there. In example 1, we're trying to find the configuration for sulfur. To find the electron configuration for sulfur, we would first find sulfur on the periodic table. So there it is. So then we got to figure out, okay, I'm going to work backwards. So I'm going to go through backwards on the atomic number. So 16, 15, 14, 13, 12, 11, 10. That's going to be my first noble gas, the previous noble gas before it. So I'm going to put neon in brackets. And then from there, I'm going to start doing my electron configuration. So sodium and magnesium, that's the 3s. And there's 2 blocks. So I'm going to have 2 electrons in the 3s. So 3s2. And then sulfur is going to be 1, 2, 3, 4 Okay, so it's 4 electrons, and that's the 3p, so it's going to be 3p4. So the outer shell is shell number 3, and it has 6 electrons in it. So that's the noble gas, or the abbreviated electron configuration for sulfur. Look at example number 2, zirconium. We're going to do the same thing. We find zirconium. The symbol for zirconium is Zr. It has 40 electrons, 40 protons, therefore 40 electrons. So we're going to work backwards. So 40, 39, 38, 37, 36 is going to be our first noble gas. Remember, group 18 is our noble gases. So it's going to be Kr, krypton, in brackets. And we're going to start from there. So this is 1, 2, 3, 4. This is the 5th row. Okay. So it's going to be 5s2. And then zirconium right there. Yttrium and zirconium are in the 4d. So that's going to be 4d2. And likewise, we want to put it back. We want to put it in order by the shells. So the final notation is going to be 4d2, 5s2. Shell number 5 is going to be the outer shell. It's going to have 2 electrons in it. Okay, so the electron configuration for zirconium is krypton 4d2, 5s2.
How about a joke, Mr. Harbinger?
Okay, Bandit, what's your joke?
What do you call 1,000 cats at the bottom of the ocean?
I don't know, Bandit, what?
A good start. Ha ha.
Bandit, that's not very nice.
Cats think they're so smart. I once had a cat tell me that onions are the only food that can make you cry, so I hit him in the face with a coconut. Ha ha ha.
Bandit, be nice. Anyway, back to the chemistry. In orbital notation, the individual orbitals are drawn as a blank, a circle, or even a box, and up and down arrows are used to represent the electrons. The Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. In other words, 2 electrons in the same orbital must have opposite spins.
So you can't have 2 up arrows or 2 down arrows in the same orbital?
That's correct, Bandit. Also, Hund's rule states that degenerate orbitals each get 1 electron with an up spin before any orbital gets a second electron. Remember, degenerate orbitals are orbitals with the same energy value, and that p, d, and f subshells contain 3, 5, and 7 degenerate orbitals respectively. In example 1, we're going to look at the orbital rotation of oxygen. Okay, so oxygen is boxed in blue right here, so we know we're going to go through the 1s, the 2s, and we're going to stop in the 2p. Okay, so we're going to use blanks to represent our orbitals. So I'll draw a blank to represent the 1s subshell. Okay, and that's a lowercase s. Okay, s's can only have 1 orbital in them, so I draw 1 blank for that. I put an up arrow in to represent the first electron, and a down arrow to represent the second electron in the 1s. Then after the 1s, we have the 2s. Again, it's an s-type subshell, so it has 1 orbital, so 1 blank. So I'll draw an up arrow and a down arrow. And then we're going to do the 2p. Now the 2p has 3 orbitals, so we're going to draw all 3 of those. So I'll draw 3 blanks, and I label each one as 2p. Sometimes you'll label these as, you'll see them labeled as 2px, 2py, 2pz. Okay, so now we have 4 electrons used up. Oxygen has an atomic number of 8, so it has a total of 8 electrons. Okay, so I'm going to keep track of my arrows. So I'm going to put 1 in each orbital. This is Hund's rule. It says that each orbital gets 1 before any gets a second when you're dealing with degenerate orbitals. So the 2p subshell has 3 degenerate orbitals. They all have the same energy value. So that takes care of 3, but I need 1 more, so I'm going to put 1 down arrow in the first blank. We count our arrows, we get 8. It has 8 electrons. So it's this 1s2, 2s2, 2p4 is what the electron configuration is. And so these 2 blank spots represent 2 spots that this atom needs electrons. Our next example is going to be iron, symbol Fe. Okay, again, it's boxed in blue. So we're going to go through the 1s, the 2s, the 2p, the 3s, the 3p, the 4s, and part of the 3d. So the 1s
we know everything before we get to the 3D is going to be full. So the 1s is going to have 2 electrons in it. The 2s, remember the s's only have 1 orbital, so they get 1 blank. And the p's will have 3 orbitals. So we're going to put 1 in each one. And we're going to go back and put the second one in. And then we have the 3s. It's going to have an up and down arrow. Then the 3p. The p-type, so the p's have 3 orbitals, so we draw 3 blanks. So I put 1 in each one. Then we go back and add our second one. It's always a good habit to get into is when you have degenerate orbitals to go ahead and put 1 in each one and then go back and fill them, because that'll help you remember that they all get each one gets 1 first before any gets a second. So then the 4s is going to have 2. Then the 3D, it's a D type, so it's going to have 5 orbitals. So I'm going to draw 5 blanks. So 3D, 3D. Okay, so now we got to figure out how many into the 3D are we going to go. 1, 2, 3, 4, 5, 6. So 6 electrons in the 3D, so there's 5 blanks, so each one's going to get 1. And then we come back and we fill in the last one. Okay, so that's the electron configuration for iron. Did you hear about the 5 cats riding in the back of a pickup truck that drove off into the lake? No, I didn't hear about that. They drowned because they couldn't get the tailgate down. The electron configurations of some elements don't match the expected electron configuration. For example, chromium's expected electron configuration would be argon 3d4 4s2. Its actual electron configuration is argon 3d5 4s1. As it turns out, half-filled and filled subshells are stable configurations of the atom. So in some circumstances, atoms will rearrange their electrons to lower the total energy of the atom. If you are in honors chemistry, you will need to know which elements do this and what their actual electron configurations are. So that brings us to the end of another episode of Chemistry with Bandit. Hope you will join us again next time. For now, this is Mr. Habiger and Bandit saying, Vaya con Dios, my friends, and don't be afraid to tell bad jokes because all the good ones are gone.